today, let me tell what I was doing last time. Okay? I was looking at this Lagrangian. Right? And here the spin of the problem was lambda g. So spin SI was defined by this equation, where G is an element of SU2. Okay. Now I want to understand, okay, how starting from this Lagrangian I can perform canonical quantization and show that it is really describing a particle of fixed spin given by some lambda, where this SI fulfill angular momentum commutation relations. Okay. Now here we notice that this L, okay, generally in the problem here L is a function on, let me call it M, which in this case is SU2, okay, and velocity is on M, okay, and so if these are coordinates are G and these G dots. So actually we can say that this L is a function on the tangent, okay, let me call it bundle Tm, okay, this is TSU2, whose coordinates are G and G dot. So what I mean by the way, tangent bundle is also a bundle. Okay? So what you do is on the manifold, so the tangent bundle is obtained by taking the manifold, in this case SU2, and at each point you attach the tangent space, then you take the union. Okay? And one can show that there is a this is natural bundle structure also. But never mind. What I want to tell here is that the Lagrangian that we are dealing with is a function on SU2 and velocities on SU2. Okay. But the equations of motion is on S2, the two sphere, okay, spanned by this S. It has no natural configuration space structure. That is, this is, okay, we cannot identify a configuration space. Okay, on S2. Okay. What we may call a classical configuration space. There is no natural way of finding a Q here. So question is, how do I go from this L, okay, to the S, okay, which has somehow lost track of this? How does this structure we have here in L show up? How does it get transmuted into this new thing here? That is what we would like to understand. Okay, and this what happens is somewhat non-trivial, and we will see along the way. Okay, so we want to see, okay, we want to see how to quantize L. starting directly from L. And we will see, okay, this is possible only if lambda is quantized. So this is the first instance where the classical Lagrangian admits quantization only if some parameters which come there are also quantized. Okay. This will happen in magnetic monopoles, but if you keep going along the thing, it will happen in conformal field theories and it will go on and on. But this is among the simplest instances of where this phenomenon happens. We will not be able to quantize this unless this parameter lambda gets quantized. Okay. What those quantum values are of lambda, we will see. I mean, we will see that the quantization is not really unique. Okay. So depending upon how you manipulate it, you get somewhat different values, but for large values of this lambda they coincide. Okay. Okay. Now how do I do it? So for this purpose we had to go back, okay, to some generalities. So I want to start with Dirac's. Okay. I should say probably Dirac-Bergman theory of constraints. Now, the first fact is, given a manifold M, for example, like SU2, okay, associated to it we have two structures. Okay. We have two structures. Okay. One is what is called Tm, which is the space of positions and velocities. Okay. So let me call it m dot, okay, on M, or this is that I may call as tangent bundle. On M. So here it's not a principal, it's a bundle, but not a principal bundle. That is, if you give me two of these points, I can naturally project it to M. Okay. So at each point M, what you have got is a whole vector space sitting there. Right? This M dot can take all values on the tangent, so it's a vector space that is sitting there. Okay. And you can project it to the first entry, and that will be a projection map. So you have a bundle, but it is not a principal bundle because there is no group action that you can associate naturally, so as to get rid of this M dot. Okay. So, but anyway, I want only the language. Okay. The Lagrangian, let me not talk about Lagrangian. Okay. Then associated to Tm, okay, there is another space T star M, which are space of positions and momenta in our language. Let me call it M P, okay, on M. Okay. This P, at each M, the P's are spanning some vector space. Okay. These are momenta. The momenta, okay, P, which I can call with lower coordinates in some coordinate system, are dual to the M dot I, the velocities at M. Okay. So at each M you have the vector space of velocities. Okay. So if I put the index here upstairs, the P's are the dual space, that is linear functions. I mean, these are the ones with which you can contract these two. Okay. So the momenta P sitting at M are the space of duals to the velocities sitting at M. Okay. You have to sit at M because the vector space may change. For example, if you take a sphere, the tangent space will keep changing as you keep going. Okay. So you cannot take this P dot Pi sitting at some point and apply it, think of it. So you have to think at M, at a given M you can do this. Okay. When you contract it, you get a number. Contract Pi with an M dot I, you get a number. Now the second fact is the following. Okay. Fact, okay. T star M, okay, say functions on T star M have a priori a Poisson bracket defined. Okay. This is independent Lagrangian or anything, it is given. Okay, I will show you if you want. Let me first give it to you in local coordinates. Okay. If I take two functions f1, f2, the Poisson bracket at qp, I called it mp, is going to be summation, okay, usual thing, df1 dmi, okay, df2 dpi minus I extend f1 with f2. We have some question I could see. I can write it globally. So this is the standard Poisson bracket. The statement I am making is you don't need until now there is no Lagrangian or anything, equation of motion or anything. These are all there. Okay. What actually this is, so it's a Poisson manifold. What they call Poisson manifold. This Poisson structure is coming from a symplectic structure, okay, or a Lagrange bracket, and now this is coming from a PDQ. Okay. This is coming from a one form, okay, on T star Q, which locally is, let me not worry, is this one form. Okay, you can define what this is also intrinsically. If you take a point at T star m, okay, it's a this is a one form living on T star m. Okay, so the one form omega at the point, so a point of T star m will be m p, right? T star m has a natural vibration, that is p's are sitting vertically up, so it's a one form. I am looking at the one form at the point p, omega and p is on T star m. Okay, I had to give you the value, some of you may know different on vector fields. Okay, so what this is that evaluated on this vector field do dmi. So if I take a vector field with coordinates mi d over dmi, so alpha I d over dmi, is defined by, this is the rule is, this is a one form. I am giving, now I am taking a vector field. The vector fields can be thought of as generated at that point by things which are tangent, these things on the base, and also there are vertical ones. Okay, on this what you do is you apply p on this and you write this as pi alpha I. Huh? This is not Hamiltonian. PDQ. I am trying to tell some of you, maybe this is not a good thing to say. I am trying to tell how this one form comes. Okay? The one form comes, and then if you take one more, say, the one form is living. Until now I have no dynamics, no nothing. It's just algebra. Okay? I take this cotangent bundle. Okay? I take a point of the cotangent bundle. I'll define a one form at this point or the cotangent bundle. It's a one form. So some of you may not know what is a one form is, never mind. Huh? Omega is a one form. Okay, it's a canonical one form. At a point which in local coordinates are denoted by a point of the base and a point of the fiber. I had to give the value of this one form to tell what it is on vector field tangents to the base and vertical ones. If I take a vector field tangent to the base at that point, which is going to look like this, these are the differentials and these are the coordinates, but, and I have to tell you what omega does on this, but omega is evaluated at a one form already, so I take p and apply on this here, so I get alpha API. Okay. Then I say omega mp, okay, on vector fields like say beta j d over dpj, local coordinates, I say 0. So vertically it is 0, horizontally it is given like this. Okay, this is same as PDQ. Yeah. Then if you take, huh? By definition. I had to tell what I wanted to tell, maybe it was not a good idea, how on the cotangent bundle the positions and momenta there is already a Poisson bracket and there is already stuff going on. Okay. Okay. This property is not shared by positions and velocities. Okay. So it's a one form, so it is dual to vector fields. It's a dual to vector fields. Okay. Now I had to define the one form, so that means I had to give the value of the one form on all tangents to the whole bundle. So the bundle has both directions moving along q, along the base, namely m, and also vertically. So on the base I give you this formula, vertically I say is 0. This is some vector, some tangent at that point sitting at the base at the point m.
Beta j at
Huh?
Beta j are equal to this alpha is.
Yeah, so at the point M, I am here. Huh? At this point M, okay, vector fields are, these are local coordinates. So the space of tangents are given by these vector fields. It's a basis of vector fields. So general vector field at that point is this. Okay, these are numbers, these are components, and I had to tell you what this does on this. I contract P with alpha.
That equation is just a definition of how one forms act on vectors, right?
Yeah, omega evaluated on this vector field.
I have one slot which it takes one vector field from the tangent plus gives you a number.
Gives you the number. So it's defined. And I say it is 0 on the other thing. So it's completely defined. In local coordinate, it is clearly going to look like PDM in my language, PDQ or PDM. I am using M because in the Lagrangian in our case is not a function of the configuration space. So I didn't want to use that like Q. Okay. So this is completely, now some of you again, there is this hitchin business. There is some new thing going on where these two things are put together. Tm and T star M are put together to make a grand structure, okay, which is coming, which is becoming very popular, actually inspired by some developments in string theory called T duality. Okay. So there is a way of not only considering Tm or T star M, but together both M tangents and cotangents together at each point, okay, then doing something with that, okay. Then some new stuff begin to happen, okay. This is due to Hitchin, but it has resonances in complex geometry and so on, but it comes from some developments in what people call as T duality. Never mind. Now until now I have not talked about Lagrangians. So what is the use of the Lagrangian? Now the Lagrangian given L, okay, is a function on Tm to reals. So the Lagrangian is a function on tangent bundle to real numbers. There is a canonical map. We have a map, okay, which we call the Legendre transform. Okay. From Tm to T star M. So what does it do? It takes a point M and M dot, and the image of this point is M, okay, and dl over, let's write, the point is Mi, M dot I, takes Mi and takes you to dl over d M dot I at M and M dot. So this is my Pi. Okay. So this is a mapping. It takes you from the tangent bundle to the cotangent bundle. Again, no equation of motion. I want to emphasize, none of this has anything to do with the equation of motion. Give me any arbitrary function on the tangent bundle, I can set up this mapping. Okay. So it is taking you from Tm to T star M, okay, and is normally we call it as a Legendre map. In elementary mechanics, I think it is called, I think it's called DL. I think it is called DL. No? I think so. Huh? Sorry? I think it is called, the Legendre map is called DL. I am not sure. Hmm?
It's called PDQ. Oh, you mean the
It's not PDQ. I don't do PDQ. Huh? Legendre transform. I have not done any structure. So, in elementary mechanics, this map is invertible. Okay. But that is certainly not the case for us. Sorry?
Even in elementary mechanics, what is elementary mechanics?
Like point particle are 3 dimensions.
I mean, without constraints.
Without constraints. Okay. But this is not the case. For us. Like, our eventual phase space is 2-dimensional. Okay. Tm dimension originally is 6 because SU2 is 3 T, so but eventual dimension is 2. So something has gone completely out. 2 means your 2 spins. Okay. 3 SU2 variables and 3 velocities. Okay. Okay. And eventually we have this is spin, no? So I have the Poisson bracket is Si Sj, epsilon ij k sk, but with this S squared is fixed. So if 3 is a sphere, so 6 has suddenly become 2. So something has gone away. Okay. So it's certainly not going to be the case that I can go back and forth with ease. So this happens, I think this happens in gauge series, and it was appreciated already by, if I am not wrong, Dirac appreciated it long ago. Then as I said earlier, Pauli gave this as a problem to Leon Rosenfeld, who seemed to have made a complete solution of this, okay, at the level of development then, and he applied, okay, and there is a paper. Apparently Pauli lost interest, okay. Then there was a Chinese student of Dirac, Chang, I am not remembering, who did extensive work. Then Dirac himself picked it up, and I think Dirac was the first one to tackle especially gravity, okay, which is exceptionally difficult. Say Einstein gravity. How to deal with diffuse? Okay. It's exceptionally difficult. Okay. And one should appreciate that in classical mechanics, or this is the first major development at a conceptual level after nearly 100 years or so. Okay. So it is a major thing. No? I mean, before that there were some analytic developments by people like Poincaré, Poincaré recurrences and all kinds of things. Huh? Then, but if you go back, what? Who did this? Lagrange, Laplace, Hamilton. We are talking about more than 150 years. Okay? So the idea is like, so suppose.
So how is the dimension 2 final?
Huh?
How is it 2? Shouldn't there be 2 variables?
I'll show you how it happens. What I will show you is set up the formulation, then I will go back to that Lagrangian and I will actually quantize it in front of you and show how 6 becomes 2. Yes.
So you said that there are some momenta that cannot be inverted. So that leads to be some constant. Is there some constant present that you cannot invert some momentas of?
You cannot, the mapping invert is, yeah, you can say that. The Lagrange, this Jacobian is singular, yeah, is 0.
So you cannot invert some of the momentas because of the constant there.
Yeah. I didn't put it in that language, but if you want you can say like that, because this is linear in the velocities. The Lagrangian I wrote, this Lagrangian Of course, I have still to tell you how to handle this Lagrangian. Right? It's linear in the velocities. So if you look at this double derivative in whatever coordinates you write, this matrix is actually 0. No equation of motion is involved here, so you cannot invert locally. Okay? I mean, the Jacobian matrix is 0. Okay? So already you can see trouble. You can say that way, right? Because you need this to be non-singular to be able to invert. But it is already 0. We can see it is 0. So this will happen in all first order Lagrangians. Huh?
Those Lagrangians are singular.
All those things are singular, but that is not the only way singularities will appear. All first order Lagrangians are certainly singular, but even if they are not first order, it can be singular. Sorry? Okay. Singular, nothing is singular. He wants to, he calls it singular by convention. Huh?
Zero is basically saying
Tendency is, yeah.
Some kind of a gauge invariance is emerging. Yes, but it may not be always gauge invariance, because if you do the same calculation for a massive vector meson, you will again find constraints. Take quantum field theory. d mu of mu nu squared plus mu squared a squared. That has no gauge invariance, but it has constraints. I think one of the Indians were among the Meenakshi Sundaram, is it? There was actually, I think Meenakshi Sundaram was a mathematician. There is, however, an old paper by one of the people here, Andhra somewhere, who made contributions to analyzing this. He didn't do Poisson bracket, he didn't go into the Hamiltonian formulation, but he did analyze the singularities. Okay. I mean, singularities means when the Jacobian matrix vanishes, what does it do for the initial value problem and things of this kind he did. Okay. So let me go back here. Suppose the image, okay, of this map, okay, is a submanifold given by the vanishing of functions Tj of, let me write m and p, okay, equal to 0. But j take some values. Okay. So j is some index set. So there is some submanifold here. Okay. The statement, but Tj are not identically 0 on this full T star m. It's not that T is simply 0 function. It is it could be something like m square plus p cubed is m square minus p cube. Okay. And the level set where it is vanishing is giving you the submanifold which is coming from the Lagrangian. So this implies, okay, Pj, okay, there exists f, okay, such that the Poisson bracket of Pj with f is not 0. Okay. Pj can create canonical transformations. It is just that the image is this level surface, but it could even be that if I take this surface, the Poisson bracket the trajectories of the Poisson bracket can be transversal to the surface. No guarantee that this doesn't happen. PJs themselves may not be commuting or have zero Poisson brackets among themselves. So to emphasize this, Dirac writes the weak equality Pj is like this. Okay. For him it is a warning. If you have Poisson brackets, implies in particular, don't put Pj, don't set Pj equal to 0 in Poisson brackets. It's a warning. Because there will be some Poisson brackets which are not, where Pj, where involving Pj which is not 0. Okay. Huh? Pj's are 0, not like that. Again, what it says is you have got this big space T star M, and on this there is some surface where Pj is 0 as functions, some submanifold. But the Poisson bracket does two things. They are functions, but they also create canonical transformations. Okay. But the canonical transformation generated by the Pj, I mean there are Pj's living, Pj has values here and there. It's just that this is where it is is 0. So if you take Pj somewhere else, okay, and take Poisson brackets, you will get non-zero values. Even here, if you take an arbitrary function here and take Poisson brackets, you will get different value. You may get non-zero value. For example, I don't know, take Pj as p squared minus qq. Okay. The 0 set of this is p squared equal to qq. But this the Poisson bracket of Pj is not 0 with some arbitrary function. Say with p, it's not 0. Huh?
Even on the submanifold.
Sorry?
Even on the submanifold.
Yeah, even on the submanifold, nothing. Okay. Okay. Also, Pj are called primary constraints in the Dirac language. Okay. Now comes dynamics. Until now there is no dynamics. Okay. So we want to check until now I don't need any Hamiltonian or no nothing. But we would like the constraints to be preserved under time evolution. Okay. Until now I have no time, no nothing. Okay. But we want to bring in, we want to okay, make sure that time evolution preserves constraints. In the, say if you are doing GR and you do an initial value problem, even without knowing any Hamiltonian or anything, there are constraints. If you take the Riemann tensor and take some spatial components of it, you will get constraints. So you put that as a constraint on your initial data. Then try evolving it by your highly nonlinear differential equations. There is no guarantee whatsoever that they will be preserved. In fact, in general, they will not be. Okay. unless you do some further statements. Okay. You are looking surprised. Why?
Why? In your room they are preserved.
They are, but not that. But you have to complete the constraint analysis completely. Okay. Then you can prove that locally they are preserved. Okay. Globally, again, these are all false. Because there are theorems, global theorems that if you evaluate for finite times, suddenly hell breaks loose. Okay. Unless you put some conditions like some constraints, some initial data should not be too big in some sense. Okay. So some funny equations start coming. But anyway, that is not the point. So what do I do? What did Dirac do? So consider the Hamiltonian, okay, I'll call it as QP, which will be the usual thing, PQ dot, so it will be PI QI dot, I'll write PI dot as MI dot as I told you, minus L of MM dot, okay, now plus, okay, I will add Vj of QP, Pj of Pj. This is my Hamiltonian. We note Vj is a Lagrange multiplier. Okay. I won't do the full analysis, but it is easy to see. Also, if you look at the variation of the first group of terms, okay, you can see that this is delta pi m dot I, okay, plus pi delta of m dot I minus dl over d mi delta mi minus dl over d m dot I delta m dot I. But on the image of the Legendre map, okay, so on the surface Pj is 0. On this surface, this term cancels with this. Otherwise, it will not cancel. Okay. So, okay, is some delta pi m dot I, okay, minus dl over dmi delta mi. So the variation of this function involves only delta p and delta m and p. Okay. So in fact, you can check that this implies that this h of qp or mp is h0 of mp plus the Lagrange multiplier terms. These Lagrange multipliers are put in. I will not do the analysis because these variations here on this surface, when you do this variation, these variations have to fulfill this constraint. Okay, you can only vary p and m on the surface. Okay, so this fact is taken into account by putting these Lagrange multipliers. Okay, this is evaluated on that surface. And I am now doing this variation of the Hamiltonian on this surface. I should say, I am getting confused with notation. Okay, this q should be m. In the book, I think I have written. Huh? So these are put in as Lagrange multipliers to take into account that the variations have to fulfill delta Pj is 0. Okay.
Small confusion. Is a function of QP or MP is also
I am getting confused. I should write all the time m. There is no meaning. The reason I start with m is the Q configuration space as we know it in all the problems we consider disappears. Okay. There is no configuration space that not recognizable configuration space. There is no configuration space. There is a phase space. Okay. So in that case Q is misleading, I thought, because capital Q is normally thought of as a configuration space. Okay. So I will use M for whatever the manifold is that enters the Lagrangian and whose velocities and that manifold and this velocity that enter the Lagrangian. So I put in this thing. Okay. Now so calculate cross of bracket Pj H, okay, and set it equal to 0. Okay. So this is the statement that time evolution preserves the constraints. This gives secondary constraints. For example, if you do it in electrodynamics, which is a good example, you will find that the primary constraint in electrodynamics is that the momentum conjugate to this, if you have the electromagnetic potential is mu, momentum conjugate to A0, you will find this weakly 0. I am just telling, okay. Then if you look at the secondary constraint coming from P0, you will get the Gauss law. And you will find no tertiary constraints, it will stop there. Okay. Similar things will happen with massive electrodynamics and QCD and gravity as well. In fact, in the Fierbayan formulation of gravity, you will get even more complicated scenario for constraints. Okay. Keep going. Okay. Until all constraints are gone, okay, till all constraints are, okay, no more constraints are generated. Set it weakly 0, compute a pause of bracket and then evaluate it on this surface. Okay. So when I write here 0 is modulo the piece. Okay. So it could be some linear combination of piece, but there will be maybe extra terms. Okay. That will give you the secondary constraint. Now you take again, then consider them modulo the constraints you already have. Okay. That will go on reducing, it will go on putting more and more equations on which you can perform a initial value problem. I mean, you cannot define dynamics unless you go on restricting the part of the phase space you are looking.
Okay, and what is primary and secondary?
Primary is the one which you get right away from the Lagrangian. Okay. From the Legendre map. It goes into some submanifold that doesn't involve dynamics even. Okay. All the others are sensitive to the dynamics. Okay. Now, so now you have got all the constraints. Okay. Now, assemble all constraints as Ck be equal to 0, k going from over some index set, some number. Okay. Now I will give Dirac's definition. For him, primary, secondary are less important than the definition I give you. Okay. Dirac divides the constraints into first class, okay, when we call it Fk, and to second class, which I will call Si. The Fk's by definition fulfill the Poisson bracket of, say, Fi with Fj isCijk Fk. This is a strong equation. I am not putting, it's equal. The rest are second class.
So you can find an algebra on the
Well, these things here in general will not be even constants. Okay. I mean, it is true that in my case, in our case, they will be the structure constants. They will have a nice interpretation. Okay, they will be constants and nice interpretation. But in general, that's not true. For example, in quantum gravity, if you take what they call the time evolution constraint, what is it called, the quadratic constraint, and look at its Poisson brackets for different q different test functions, different smearing functions, you get something, okay, where the coefficients themselves depend upon the points. Okay, so it is not an algebra, it's not a Lie algebra or anything. Okay, so you don't know what it is. Jacobi is okay. Modulo constraints. Jacobi is because Poisson bracket fulfills it. But there is no characterization of those things in terms of Lie groups or anything. Sorry? Poisson bracket of? It is can be 0. Yeah. So some structure constants can be 0. Okay. So what I will try to do, I should soon leave today, but I will analyze next these two, and I will show you that in the Dirac approach, these F's are so Dirac identifies these F's as a phase space version of gauge transformations in the Lagrangian framework. Okay. So these are constraints which he will put as conditions on the quantum states. I will show it to you. Whereas the second class ones, there is a way to completely eliminate them from the very beginning. Okay. So I will discuss what is special about this second class. Okay. They are somewhat simpler to treat. Okay. Well, this one is quite difficult. Okay. In fact, I was very careful in formulating my statements that they are the phase space version of what happens with gauge symmetries in the Lagrangian framework, but the way they turn up here can be very obscure. Okay. You will not be able to do, you thought you knew what is a gauge transformation or the diffeomorphism, and you tried looking at it here, you won't recognize. It will take you 2 days to figure out what has happened. Okay. So this is quite important, and I will come and I will treat it, and but I want to tell you one thing, just as my last statement. care is necessary. There is no guarantee that a variational principle will give consistent equations. There is absolutely no, we think that is coming from an action, so everything should be okay, by varying. And the example you may want to check is the following. Use, for example, L equal to Q dot, L equal to Q, for example. I give you two examples. This will give you one equal to DL over D. This is not good. This one, take this. L equal to Q. Okay. This will give 0 equal to 1. Right? ddt or dl over dq dot is 0, dl over dq is 1. So this is giving you 1, 0 equal to 1. Okay. So if you do this and do a Hamiltonian this analysis, you will find that there is no phase space left. It's a good exercise. So variational principles are no guarantee that everything is okay. Sometimes you see this statement in the literature. It's not true. Okay, I'll stop here, but next time I will do this, finish the constraint analysis, and I'll do the spin system, which is quite instructive, and we will show immediately that this gets us into this whole masala about higher state representations. Okay.
Simple example of Hamiltonian constant system.
About?
Hamiltonian constant system where Hamiltonian
Hamilton itself is 0. I will do it. Yeah, I will do it. I understand. So my progression here, the Hamilton is 0. Here is 0, and I will in my progression, next progression from here will be magnetic monopause. Then I will do Chern-Simons, where the Hamilton is 0. Okay. So, but something happens if you put a manifold with a boundary. Okay. So I will discuss that, and because after also it has good physical applications. So I'll do that. Okay. So this has 0 Hamiltonian because it's a first order in time, right? So whenever you have first order action, Lagrangian, Hamiltonian by Legendre transform is 0. So this part here is 0. Only this is left. Just the constraints. So the entire thing is coming from the constraints.